So 8.4, stretching and compressing materials. Like we talked about last time, most materials can be modeled using springs to represent the molecular and atomic bonds that they have. So those bonds are actually quite stiff. If you look at the picture here, they're representing the atoms and bonds that they share with little springs in between them. And so, but they're stiff, but they can be stretched and compressed a little bit. So if we take a look at the figure A now, we have a little rod connected to a clamp. Very simple picture. But if we pull on that rod or push on the rod, it will very, very slightly stretch or compress based on whichever way we're going, right? And that is because the particles inside or the atoms inside of the rod are going to stretch and compress a little, just a tiny little bit. So there is a restorative force inside of the rod. So in B now, the real data is actually shown for a steel rod that we are stretching or compressing. If we were to hook it up to some sort of a measuring device to measure how much deflection there is based on the force that we've put on the rod. So we apply a force, either stretching or compressing, and we measure how much additional length the rod has or how much it compresses. So this is real data, and the rod does behave like a spring. So if we notice, though, the scale here, this is in kilonewtons. So kilonewton is every 1,000 newtons. We get 1 kilonewton. So as if you notice, the change in the rod's length is also in millimeters. So we're not getting a whole lot of stretch for every kilonewton, but we do get stretch. And if you notice, this is linear, which means that is a K value. So it does act like a spring. And the K value is extremely huge.
Steel rod.
This is for the steel rod. And as we talked about last time, a very large K value means very stiff spring, right? And that's what we would expect for the steel rod because it's not like a
Because at
slinky.
that point, if you're pulling with so much force that you're stretching it, doesn't it end up just deforming it and then breaking the rod?
It would restore. So we are not seeing the linear relationship here breaking down. So that means that the rod would go back to its original shape.
Okay, well, just what happens when it bends?
So what happens when it deforms is we would see a departure from this up here somewhere. We would see a departure from the spring.
So would it drop?
We would see something. Okay? We just don't know what that something is at this point.
I figure if we break it, it's going to go straight down to zero.
Well, okay, yeah. If it breaks, then it broke, and the graph is done, right? But when the object deforms, we see some sort of departure from the linear graph that we're seeing here, and then the object will never go back to what it was before, like the slinky, right? It's been stretched to the point where it doesn't go back. And then on the slinky, you know, if it was like a green slinky, let's say, speaking from experience, the plastic green slinky, at that point of deformity, it's no longer green either. It's like some sort of off white, maybe a little bit of green still. It's been completely deformed. It's never going to go back, right? So we had this relationship here, the linear relationship, but then at that deformity, this has happened here, okay? We just don't know exactly what that looks like yet. So anyway, tremendous amount of force to get the rod to extend, just 1 millimeter. So this is a very rigid material, not elastic, like we were talking about yesterday, like the rubber bands, okay? Rubber bands, the elastic material is called pliant. It's very easy to manipulate. It's very, the spring constant there would be very small. Okay, so the next screen has a lot of words also. We have the rod again, a bigger picture this time. We have the original length of the rod, L. We have the restoring force. We have the delta L. So we're pulling on this rod away from the clamp or the wall, whatever it's affixed to. we have the surface area A here. Okay, so the stiffness of the rod depends on the material. Also, you might expect that the longer object would be easier to stretch than a shorter one. That is true. Longer object, easier to stretch. There's more length to it in the first place, so we get a little bit more stretch out of it. Finally, an object with a larger cross-sectional area might be harder to stretch than a skinnier one. Does that make sense?
Yeah.
Yeah, absolutely.
Takes
Okay.
more force.
So, couple of concepts there. Stiffness of the object depends on the material. So that's one thing. Longer object, easier to stretch. Larger cross section, harder to stretch. So we got three concepts right there. So experiments reveal these ideas to be true. The spring constant of a rod can be written as this equation right here, and we're about to get a new constant. This y is called the Young's modulus. This is a property of the material. It's just a property of the material from which the rod is made and does not depend on the shape or size. It's just what is the material? It will have a Young's modulus associated with it. A is the cross-sectional area and L is the length of the rod. So a larger Young's modulus indicates a stiffer material. On the chart on the left, we have a bunch of Young's modulus for rigid materials. Cast iron has a Young's modulus of 20. Notice the units though. This is times 10 to the 10th power newtons per meter
So that's
squared.
very large.
Yeah, very large numbers. So 20 for cast iron, and then steel is also 20. Silicon is 13, so it's falling. Copper is 11, a little bit more pliant. Aluminum 7, even more pliant. Glass 7 also. Glass is actually kind of like a liquid. It's very bendable under the right conditions. You can heat it up pretty easily, and then it bends. Concrete 3,
That's
and then wood. So this is specifically Douglas fir. Obviously, there's lots of different types of trees.
Ever blown glass?
nope.
So
Neither, but I've
wood is
watched videos.
bendable, really, if you think about it.
Yeah.
So the restoring force for spring equation from earlier and calling the change in length of the rod delta L, we have this formula for force. Force equals Young's modulus times the cross-sectional area divided by the length. And that would be the original length and then times the change in length. And this applies to both stretching and compressing. And we're about to do something with this formula. It is useful to rearrange that equation that we just saw to this format. So we have the force divided by the cross-section area, and then the y on the outside of this group of delta L over L. So note that the delta L over L would be a unit of length divided by a unit of length, so that is unitless. Then Young's modulus, if you remember from the chart, has units of what? Newtons per meter
Is it square?
squared. And force is units of newtons, and area is per meter squared. So we have newtons per meter squared equals newtons per meter squared on both sides, right? So now this is a force per unit area equals a force per unit area. So if you think about that, like as I press a force onto something, it's the force being distributed over a area that the force is being applied to. Okay? Can you picture that?
So is that kind of like with snow? Like when you have snowshoes, the bigger the area, the
Oh
less-
yeah. So like a good example, I have my body weight as I'm wearing just shoes versus my body weight as I'm wearing snowshoes, right? Now my body weight is being distributed in my snowshoes over a broader area, so the snowshoes are supporting my weight, distributing that force over that broader area, and the snowshoes are supporting my weight in the snow. That's a great example. Okay, so the distribution of the force over a point area versus a broader area. Okay, so we have this F over A is a very important thought here. Okay, and that's why it's useful to write the equation this way: newtons per meter squared on both sides. So, and that's this only, right? Okay, so the ratio F over A is the ratio of force to cross-sectional area, and that is called stress.
So the bigger you are, the more stressful you are.
The bigger a force applied to a smaller area, the more stress you're putting on that smaller area. If the stress is due to stretching, it's called a tensile stretch because the stress is due to stretching. It's called the tensile stress, but we can call it a tensile stretch also, okay? So tensile means I'm stretching, and so therefore we have a tensile stretch or a tensile stress. The ratio delta L over L is called the strain. It is dimensionless, as I mentioned, and it's the fractional change in the rod's length. So it's almost like a percentage change, right? How much did I change compared to how much was the length in the first place? So we have stress versus strain now in this equation. And in the world of physics, in the world of engineering, stress and strain are massively important concepts. Okay? So you're looking at something that is incredibly important in our world here in this equation. So because the strain is dimensionless, Young's modulus has the same dimensions as stress, which is newtons per meter squared. Okay?
Times 10 to the 10th, right?
Times 10 to the 10th for Young's modulus. Don't forget that. So the number that you saw, 20 or 13 or whatever, was times 10 to the 10th power, newtons per meter squared. Okay? So that's the idea. Just conceptually, I'm applying a force here. I'm applying a force here. The force is the same in both cases. Which one has more stress?
The smaller force.
They're both the same force.
Or the smaller
The bigger-
area.
The smaller area has more stress because the area is in the denominator. As that number gets smaller, the overall fraction gets larger. Okay? And the stress is the ratio F divided by A. So if I have a smaller area here, I'm creating more stress on that area. Okay? All right. So a pendulum consists of a 120 kilogram steel ball that swings at the end of a 6.0 meter long steel cable. The cable has a diameter of 2.5 millimeters. When the ball was first hung from the cable, by how much did the cable stretch?
Okay.
Well, it's a steel cable, so it's 10
Mhm.
to, or
20.
20 to 10.
20 times 10 to the 10th newtons
Yeah.
per meters.
Okay, so we know Young's modulus. That's right.
So y equals, we might want to write that down.
We'll write it down because we don't really need to write anything down except for the formula. The formula is going to be the guy that we're just working with,
Yeah.
but what is it we're looking for? What is the thing that we want?
We're looking for the stretch.
The-
delta.
We're looking for delta L. That's right. By how much did it stretch? That's the delta L. So the equation that we have is F over A equals Young's modulus times delta L over L. We're looking for delta L. So I want to solve for delta L, which means I'm going to take
If we
this.
use the other equation, wouldn't that one be easier?
This is the form that we want to know. Okay. So I'm going to divide by y. So I have F over A. I'm going to divide by y. So that puts the y in the denominator. And I'm going to multiply by L. So that puts the L in the numerator. And now I have delta L by itself. Okay. And now plug in everything because we know everything. We know the force will be the 120 kilogram steel ball times gravity. So 120 kilograms times 9.8 meters per second squared.
Wait, the cross-sectional area is like the diameter, or do we...
We'll have to calculate the cross section area. Now the length, the original length of the cable,
Was 6.0 meters.
okay, 6.0 meters. Now that takes care of the numerator. Young's modulus, you guys just told me. What was it again?
10 or 20 times 10 to the
10 to the 10th, right? And that is newtons per meter squared.
meters.
Okay, now the cross-section area. We have to figure that out. They told us the cable was a diameter of 2.5 millimeters.
Did you multiply that by pi or 1/2 pi or something like that?
So we need the area of a circle.
Yes.
That is,
Or pi
2 pi r.
pi r squared.
it's pi r squared for the area of a circle. So we need the radius. So half of 2.5 is 1.25. But this is
Squared.
millimeters,
So it's going to be 0.00125.
0.00125 meters. Okay.
All right, then multiply that by 2 pi, right? Is that what we said? Squared?
Okay.
No, it's just pi squared, isn't it?
So pi r squared. So this needs to be 0.00125 meters squared. That's the radius. Now times pi. So that's pi r squared.
And then we plug all that
So-
stuff in.
What do we got?
Who's the guy who thought that pi should be 3.14155 and not 6 point whatever, like
It
the
makes you think it was a guy.
or gal or whoever? Who decided that? I wonder.
There's a reason. There's a movement to try to make a different letter be used and go with the full circle. What do you got?
0.07187.
So with significant figures, it looks like we have two of them. This will be 7,
7, that's it. Or 7.72.
7.2. And this is
That's going to be in
Meters.
meters. Should be meters, right?
yeah,
So up top, we have kilograms times meters per second squared. That is newtons divided by newtons, so those are gone. We have meters divided by meters squared. Meters squared here divided by meters squared here. Those are gone. And up top, we're left with meters there. So there's our answer in meters. Nobody would care about 0.0072 meters, though. So let's turn that into a unit that makes sense.
7.2 millimeters.
7.2 millimeters. Now, the big question is, if this pendulum is something that needs to be swinging with accuracy,
Like a wrecking ball.
I don't think a wrecking ball needs to be swinging with accuracy. But if it was keeping track of time or something, would we have needed to calculate that 7.2 millimeter drop?
Yes.
yeah.
Yes, we would have. And we would have needed to take it into account for sure. It's interesting. So, because that's significant, 7.2 millimeters. Okay? All right. So now finally we get to see the graph of what happens when we start to fail.
Oh, look, it starts to not plummet, but slow down.
If we pull too much, regardless of the material, we will eventually reach the elastic limit. So it will look like this, whether it's a slinky or a regular spring or a steel rod or your table or whatever. Okay, does not matter. We will eventually reach the elastic limit. And if we continue beyond that, we permanently deform whatever the material is. At some point beyond even that, eventually, whatever it is breaks. So the thicker rod can sustain the larger forces. The ultimate stress the material can sustain before breaking is called the tensile strength. Tensile strength has a formula also. It is F max divided by the cross-section area. And another way to write that equation is tensile strength times the cross-section area. So it's kind of weird. There is no letter for tensile strength. You just write tensile strength.
Can we do TS? Can we shorten it?
Some guy's abbreviated name, his initials, TS times A, TSA, airport security.
Yeah.
No, It's tensile strength. Don't try to change physics. So we have in the graph, we have our regular linear slope that we've been seeing right here. That's where we find our K value. Now, that's our linear region. That's where we are elastic. Okay? Our general elastic area. Now, up in here, the rod or whatever it is, this region right here, is still going to return. We're not really linear. The rod is going to return to its original length, but it has, in my mind, actually, without getting into it, you're going to have slightly deformed it, right? If you picture your Slinky, the Slinky, when you first bought it, nicely compresses down. It has no issues, right? Like it compresses down. There's no gaps in anything. If you stretched it a little too far,
It's gonna have gaps.
now it has that little gap in it. And you're like, what the heck is that, right? And it never
What the heck
really
is
comes
that?
back quite right. It's not broken. It's not totally deformed, but it never quite comes back just right. That's this region right here, okay? You went past the linear region just enough that you slightly deformed it. It's not broken. It still works, but you did change it just slightly, okay? Now, here is the elastic limit. Beyond that point, you are changing it. You have deformed it. It's not broken. It is deformed. It will never return back to the way it was before. There's nothing you can do about it. It will last for quite a while until finally it reaches its breaking point, but it will never come back to normal. Once it reaches its breaking point, it's over. Obviously, it's broken. Okay? So it's bent, but not broken, right? So that's the idea in this graph. Now you finally know what it looks like officially. So we have some tensile strengths of rigid materials in the table. Polypropylenes. What is polypropylenes? Plastics, right. Tensile strengths, notice the units here, newtons per meter squared. We know what tensile strengths are. We talked about it earlier, where that word comes from. So polypropylene, 20 times 10 to the 6th power. Glass, 60 times 10 to the 6th power. Cast iron, we're getting stronger as we go here. Cast iron is not as strong as aluminum for tensile strength. What are we doing when we're doing tensile strength?
Stretching.
We're stretching. Cast iron does not stretch as well as aluminum or steel. Steel stretches
That's why they built swords out of it.
very strong to stretch it. Okay? Cast iron does not stretch. You would not want a cast iron
Sword.
thing as far as stretching goes. It's brittle for stretching. It's strong, but it's brittle to stretch.
Cast iron slinky.
Yeah, cast iron slinky, no good.
It'd break before you could even put it in a slinky form, I feel like.
Yeah. Okay, so if the cable isn't strong enough to support the weight, you can either get a cable, this should be made of stronger stuff, so something with a higher tensile strength, or get a thicker cable, so a larger cross-sectional area.
Steel. Oh.
Yeah,
You know how many times I've taken a cable and went past its tensile strength with like a wench?
oh
Many
yeah,
times.
yep. So get a stronger cable,
So that means the thicker the cable.
thicker cable, or a different material with a higher tensile strength.
So what about carbon fiber? Where does that
Oh,
go?
we could look at carbon fiber. But would you use carbon fiber if it had a lower tensile strength than steel?
Well, does it have
No.
a lower one or higher one?
I don't know. We could look it up.
Cole, look it up.
Your phone's close.
And it would it depend on how thick it was? The answer to that is no, because the tensile strength is independent of the thickness.
Really?
Yeah.
So how does
This
that work with a thicker cable though? If the cable's thicker,
It's because of the cross-sectional area.
Cross-sectional
multiplied
area
force max.
is multiplied by tensile strength,
okay.
right?
Um,
We don't know
Well,
carbon fiber tensile strength.
It says it, but it's not like
Yeah.
I don't know what these
GPA,
mean.
You don't know what?
I don't know what these like letters mean.
GPA and PAN.
Grade point average?
Yeah, I'm not sure that's what that means.
Probably not.
Commercial carbon fibers possess high tensile strength, ranging from 3 to 7. Big G, big P, little a.
Oh, gigapascals.
Giga?
And high Young's modulus ranging from 200 to 500 GK.
So it can stretch a lot.
Mm-hmm.
So it's better than steel?
Steel.
I don't know. We'll have to look that up another time. A bunch of 80-kilogram heathens decide it would look or be fun to swing on the pendulum in the last example. So, what is the maximum number of people the pendulum cable could support?
Well, we know that.
It's a fun problem.
What was the cable made out of?
It's
Steel.
yep. So,
We know it's.
And we know.
can we calculate its tensile strength?
Yeah, because
What
know
is
its diameter. So we know
And
its
the
cross section
Fmax.
area.
And the force is equal to the weight of each of the people.
So
there.
it's typically going to be 1,000 times 10 to the 6 newton meters.
Right there,
times-
1,000 times 10 to the 6 newtons per meter squared. That's tensile strength.
Times the cross sectional area, which we calculated,
Which is
which is
0.00125
yeah,
squared times 5.
What was the cross sectional area?
0.0125 meters squared times pi.
Okay, so what was it? What does that come out to?
I don't know.
0.0125 squared. Point 0.00005. That's what I got.
And then multiplied by the
So that is 4.9 times 10 to the negative 6th meters squared. I'll just help you out with that one. Okay, so now it says, what is the maximum number of people the pendulum cable could support? That means we need to figure out
How many
This.
newtons it can support?
F max, how many newtons it can support.
I'm gonna go with 4.
So we have the
2.
cross sectional area and we have the tensile strength.
We just multiply
So
together.
we can multiply those together. So F max, multiply them together. You can use your two answers that you already have, or the answer that you have times 1,000 times 10 to the 6th. What do we got?
Okay.
And then when we get this, are we gonna have to?
We're gonna have to calculate 80 times 9.8.
Yeah.
We can hold 40 technically significant figures.
Tell me the number you got.
4908.74.
Okay. That's the exact newtons that we can hold. So we're still using our calculator's answer. Now, the
6.
cable is also holding the ball.
Oh, so we have to add that into play.
He's
Well,
also holding
so the ball has a mass of
120.
120 kilograms times 9.8. So we got to come up with those newtons. So the mass of the ball was 120 kilograms
4. I was right.
times now. So then this will be that times 9.8.
Which is 1176. So we subtract that, right?
What was it? Sorry,
76.
Thank you. Newtons. So if we put those together, we have, no, subtract it.
Yeah.
You're right. Subtract it.
We get 3732.74.
Okay. So the amount of mass or the amount of newtons for people, we're going to subtract those two things. And we have, tell me again,
3732.74.
This is the allowable newtons that we can put on there before the cable snaps.
And you're gonna get around 4.8.
Well, what do we need to do here?
Calculate the newton, the weight of the, how many, like,
Heathen.
yeah, heathens. I love that word.
So
that's
mass max would equal these divided by 9.8. Let's get gravity out of there.
Why would you divide it by 9?
F divided by G. Because I want just the mass, because we're given 80 kilograms up here. 80 kilograms per heathen. So if I get rid of G, we'll have just kilograms, and we can divide by 80.
Yeah, they are pretty big.
I'm getting a little informal with the way I'm doing this, but whatever. So we have mass, max. What do we have for mass then?
8. 380.
380 exactly.
892.
Okay, 380.892. And this is now kilograms. So we can accept 380.892 kilograms worth of heathens.
Divide that by 80.
Okay.
We can hold 4.76, but technically, significant figures, we could hold 5 here.
Right. Significant
Right.
figures makes it 5. No, we're not going to do that. So without breaking the cable, we can hold 4.8, you said?
Yeah.
Roughly 4.8 heathens, but that will make it 4 without breaking.
Good thing there's only 3 in this class.
Well, you guys are not 80 kilograms, I don't think.
How many pounds is that?
Well, actually, you might be. 2.2 pounds per kilogram. So this would be
I'd say
160 plus.
176.
Yeah.
I'm under that, so we can hold me. He's under that, so I mean we could fit more than just
Yeah. All right.
No, that's not right.
Suppose we take equal lengths of spider silk and steel wire,
6 kilos.
stretch each, and measure the restoring force of each until it breaks. Spider silk and steel wire. The graph of stress versus strain would appear like this figure. Stress for steel and spider silk.
So you can't strain the steel that.
They both have the same breaking point.
Is that actually true?
That's true.
But you can strain spider silk more than what you can.
You can strain spider silk more than you can strain steel. You can stress them the same amount. So a strain of 1.0 corresponds to a doubling in length. So the spider silk will stretch a long way. Steel will not.
It'll double in length before it breaks.
Yes. Both materials fail at approximately the same stress. So that means they both have about the same tensile strength.
That is
These
crazy.
spider
Which is
silk made out
amazing.
of polymers?
Plastic?
Nah, it's
Yeah.
made out of body parts.
So it's amazing. Spider silk has the same tensile strength as steel.
So like if
It
you
is
have a piece of steel with the same cross sectional area as silk, is that what it's saying? Would they have to have the same cross sectional area?
Equal lengths of spider silk and steel wire. And you stretch each, measuring the storing force of each until it breaks. This is the graph that you would get.
Why don't we build stuff out of spider silk then?
Because spiders are gross.
I agree. They're scary is what they are.
So many pliant biological materials share these characteristics like spider silk does. They undergo significant deformations without failing. Tendons, arteries, spider webs. Why don't we build bridges out of our tendons?
'Cause that's
That'd be
We
nasty.
can just have human farms that are specifically to generate arteries and capillaries and human tendons and cartilage and stuff, and then we can build things with them. How's that sound?
Perfectly
Sketchy.
ethical.
Yeah, we can't do that.
It's perfectly ethical.
Sounds very inhumane.
No,
Very ethical.
can't do it.
I don't know what you're talking about. Do it.
they already have body farms.
Body farms?
Yeah.
No.
Hey, if people.
Hey, by the way, there's people listening all over the internet in the world. We're totally joking
Hey.
right now.
Hey, I'm talking about like
Oh.
places where people donate their bodies after they died to be studied in their decomposition rates. That's what a body farm is.
No,
Olivia
we're not doing that.
science.
Okay. So bone is generally a rigid cylinder. So we can model this bone as a rigid cylinder with a spongy material inside. Most of the structure of a bone is in the outer portion of the bone. This allows the bone to be more lightweight while maintaining most of the rigidity. Bird bones are an extreme example. Birds fly because they're very light, even though they still have bones and all that. Below are some examples of Young's modulus and tensile strengths for some biological materials. So on the left, Young's modulus for biological materials, we have tooth enamel. Young's modulus is 6 times 10 to the 10th newtons per meter squared. Compact bone, 1.6. So tooth enamel is very hard compared to compact bone. Spongy bone, 0.02 to 0.3. So way less hard. Spider silk, 0.2. Tendons, 0.15. Cartilage, 0.0001. And the aorta, which is the primary blood vessel in our body, hopefully you guys have learned that, 0.00005 on the Young's modulus. So
Very stretchy.
very stretchy. That's right. So then tensile strengths. So we went Young's modulus in the left. Now tensile strengths for biological materials. Spongy bone, 5 times 10 to the 6. Compact bone, 100 times 10 to the 6. So what does that mean?
Stronger.
Can I stretch it?
No,
Not really. Tendon, 100 times 10 to the 6th.
it's the same.
Spider silk, 1,000 times 10 to the 6th. So spider silk, tensile strength, very, very strong.
You know what we should do? We should like infuse spider silk with our tendons. Then we could be more stretchy.
All right. Oh, hey, look at that. Or
Already solved.
actually,
Hey guys, the answer is 0.00089.
don't look at it. Yeah, stop looking.
0.1%. That's the answer.
All right, so the femur, our thigh bone, can be modeled as a tube of compact bone for most of its length. So that's what we're going to do. The cross-section area of the compact bone of the femur of a 70-kilogram person. So that would be like,
150 pounds.
sure, 150 pounds, 160 pounds maybe, is 4.8 times 10 to the negative 4th meters squared, which is typical. If this person supports his entire weight on one leg, what fraction of the tensile strength of the bone does this stress represent? And by what fraction of its length does the femur shorten?
So compact bone.
Which means it's gonna have.
So we're doing tensile strength, right?
Compact bones tensile strength is 100 times 10 to the 6th.
Stress is
Oh,
F over A.
They give us A, like the direct, and we don't have to solve for it because it's a tube, a hollow cylinder, so they don't make you do all the math for that.
We're trying to calculate stress, basically. So we want F over A. And on the other side is
Young's constant.
Young's delta L
Delta
over L.
over L.
Okay?
We're looking for delta L, right?
No, we're looking
No,
for
in A. We're looking for
So we want F over A. So we want F over A. What is the force?
The force is his weight.
The force is his weight. So that's going to be 70 kilogram person. So it's going to be 70 kilograms times 9.8 over the area, the cross-section area. They told us, they actually just gave it to us right here.
A times 10 to the negative 4 meters squared.
Okay, that's it. That's what we want. What is it?
It is.
Yes, a very, very big number.
1.42917 times 10 to the 6th.
Yep, we got two significant figures. So times 10 to the 6 or negative 6?
To the 6th.
6
What would it be next?
newtons per meter squared. So that is the fraction of the tensile strength. Okay, force divided by area is the stress. So that's what we wanted.
In B, we're looking for the percent, right?
What fraction of the length does the femur
Yeah,
shorten?
delta L.
So that's this side of the fraction now. Okay, so we have delta L over L. So we want the delta L over L. We can calculate the delta L over L. If I divide both sides by the y, I'll have the delta L over L by itself. The other side of the equation will be F over A, and I divided both sides by y, so I have AY on the bottom. And that will equal delta L over L. Okay? That's what we're trying to calculate is the delta L over L. But I can do so by figuring out the F over AY. Okay? And I already know the F over A part. I just need to know what the Y is so I can figure out the rest.
100 times 10 to the sixth. Because we're doing compact bone.
Yes. And so from the chart that we
Wait.
were given,
It's not that. It's 1.6 times 10 to the 10th.
okay, so I have the F over A, which I already calculated.
So you can just
I can
divide.
make this 1 over y rather than writing it the way that I wrote it. So that is just going to be the F over A that I already know, which is 1.4 times 10 to the 6th newtons per meter squared, and then times 1 over, what did you say for the Young's modulus?
1.6 times 10 to the 10th.
1.6 times 10 to the 10th, and the units are newtons per meter squared. So we have newtons per meter squared divided by newtons per meter squared, so those units are gone as they should be because delta L over L has no units either. So now we just do this calculation. This is 10 to the 6th here, 10 to the 6th here, so those are gone. So we have 1.4 divided by 1.6.
That's gonna get you.
0.875.
Yeah. That doesn't.
Is it 10 to the 6th? No, it's not 10 to the 6th, it's 10 to the 10th. Sorry.
So it doesn't go away.
So it doesn't go away. 1.4 times 10 to
Or we could
the
just go 1.4
sixth.
times over 1.6
Yeah, we could.
times 10 to the second.
the like bases subtract. So we have
Yeah.
10 to the negative fourth. 1.4 divided by 1.6 and then times 10 to the negative fourth.
Equals.
What do you got?
3.0001.
0.000088. That's what I got. 4 zeros. You're missing a zero. Oh wait, there you go.
No, I'm not. It's that. So then we move the decimal 2 spots because we wanted a percent. 0.01%.
Hey, look, it's the exact same answer they got in the other one.
All right. So that's how you do that. You're using the formula to help you get the stuff that you need. Now we have one more thing real quick. A 10 kilogram mass is hung from a 1 meter long cable, causing the cable to stretch by 2 millimeters. Suppose a 10 kilogram mass is hung from a 2 meter length of the same cable. By how much does the cable stretch this time? This can be done using the formula F over A equals Y delta L over L. What did we change?
There's a proportion, right?
Kind of. What did we change though?
Oh, we changed the length, so
The
L
L. So delta.
increased, which means that the delta L.
We went from 1 meter to 2 meters, so there's a 2 here. And
delta L decreases.
delta L went from
2 to 1, so B.
causing the cable to stretch by 2 meters in the first place. By how much does the cable stretch now?
1 meter.
That doesn't make any intuitive sense though, because if you open the length, it should be longer when you stretch it, right? So it should be E 4 millimeters.
So it was 1 and it stretched by 2, right?
Yeah,
So we had a 2 there.
yeah.
Okay. So what is it going to be?
It's going to be
4.
1. I guess I'm not saying that.
So there was 1 here, right? There was a 2 on the delta L there. Now we have a 2 here. Everything else stayed the same. So what's it got to be?
It's 2 over 2. 1.
4.
4?
Like, I'm not seeing
You're not seeing it?
I'm not getting it, no.
I think it's 4.
I stopped to think because you have a